I'm delighted to be invited to deliver a presentation to leading world experts in Kant and appreciate attending my talk. Frankly speaking, I'm not an expert in great Kantian intellectual legacy, though I dare to consider myself, so to speak, post-neo-Kantian. The reason I'm here today is to apply some Kantian ideas to modern neuroscience and reassess their powerful potential in the vigorous development of this field of knowledge. It is not original Kant. I'm not diving into the Kantian original texts. Rather, it is a shy attempt of reinterpretation of Kantian ideas due to new scientific inquiry from the neuroscience. My talk, for more reliability, was pre-recorded. Let me ask to proceed with it.
Today I'll speak about the concept of number through the lens of Kantian research program in current neuroscience. First of all, I'll make some introduction to the problem. Then I'll speak about on the genetic prerequisites for the number representation. Afterwards, I'll deal with the relationship between number and language. Afterwards, I'll discuss number sense and mathematical skills in the concept of Kantian research program. Dozens and dozens of works are considering the nature of a number, although it is still difficult, perhaps even impossible, to define with any certainty what a number is. It takes place despite the fact that the number is studied thoroughly from the point of view of various approaches and in the context of various concepts that differ in the interpretation of the phenomenon of abstraction and the nature of infinity. Among mathematicians, there is a wide range of points of views on the nature of numbers. These views extend from the refusal to recognize the number as a representation of a certain set of objects or their properties to the opposite interpretation, when the number is the abstract representation of certain sets of objects or their properties. Meanwhile, the progress of modern neuroscience opens new room to analyze the number through the lens of neurobiological features of the emergence and representations of what we mean by the number. Is a number just a mark, a kind of a sticker, a tag on some sets of objects? To what extent number just a designation? And if so, to what extent the number has a neural background? The latter possibility is quite real. According to leading neurophysiologists, the program for the study of numerical representations and brain activity developed in the context of so-called the Kantian research program. The emergence of such a program is not accidental, since Kant's critique of pure reason is saturated with psychological discourses on mental formations and his history. His theory of space can be called neurophysiological. The representations of some concepts traditionally attributed to mathematics and physics, number, space, time, in a certain close to the Kantian sense of a priori, and are bounded to neural networks that have a fairly definite localization in the brain, the parietal lobe for numerical cognition and the angular gyrus for spatial cognition. The inferior temporal gyrus is activated in the case of numerical processing and the anterior temporal area in the case of processing semantic information. Perhaps even stronger statement is permissible. Number has an ontogenetic origin. The determination of number of objects was so important for the survival and or adaptation of living beings that as a result of durable evolution, this property of the brain was fixed in the form of certain elements or models of neural networks. This approach is implemented within the framework of an idea about the innateness of a number of properties of a wide class of living beings, including humans, which were acquired in the process of adaptation to the environment. Actually, the origins of this idea can be found in Plato. Some of its elements are contained in Descartes and Leibniz, but it most fully and consistently presented by Kant, who actually opposed his concept of a priorism to the concept of tabula rasa by Locke and empiricism of Hume. Beginning with Noam Chomsky's works on universal grammar, the innate hypothesis, despite some amorphous formulations, has gained an invisible place in the arsenal of cognitive sciences. Comprehension of the number is largely lean upon this hypothesis. Ontogenetic prerequisites for the number. The evolution of living beings, which presupposed adaptation to the environment, formed the property of subitation, which refers to the elements of cognitive universality, a kind of neural archetypes. This property manifests itself in the simultaneous and accurate determination of small quantities of objects, from 1 to 4. It turns out to be inherent not only to humans, already at the stage of early infancy, but also in living beings in general, monkeys, other mammals, birds, up to the bees and fish. In fact, we mean the innate sense of number, the initial intuition of the number. Sometimes it's called numerosity, the definition of the cardinality of small sets and or comparison of sets, which, according to Stanislas Dehaene, plays an important role in the adaptation process and survival in adverse conditions of living beings. There are special neurons supporting the numerical abilities of living beings, and presence of the special neural model responsible for the phenomena of subitation. The sense of number, from the point of view of ontogenetic features, are similar to the sense of place, which meant in the mechanisms of spatial navigation, the discovery and study of which by O'Keefe and Mothes in 2014 were awarded the Nobel Prize in Medicine. The activity of the groups of neurons form a cognitive image, a kind of the map of the area responsible for the coordination system in the brain. It is perhaps the same with the neurons responsible for the sense of number, which is not only a means of adaptation, but also elementary innate quality which serves as the foundation for a person to generate and construct complex mathematical operations. The analogy with the Turing machine is conceivable, the simplest device of 3 elements which nevertheless ensures the execution of a mathematical algorithm of any degree of complexity, or maybe Lego type play, which also allows the building of the constructions, the complexity of which is limited only by the human imagination. The eminent logician and economist Stanley Jevons in 1870 and the founder of experimental psychology Wilhelm Wundt at the late 19th century tacitly implied subitation, but the phenomenon has become the subject of extensive research in the cognitive science relatively recently. A number on language. If the sense of number and the phenomenon of subitation have such a wide range of action for living beings, from babies to fish, then the question arises about the role of language in the development of formation about the numerical characteristics of objects. Information is presented in symbolic and non-symbolic form. The first form refers to the precise determination of quantities, to specific numbers, the second to a kind of approximation procedures. In any case, the perception and processing of this information by the brain take place without any pattern of natural language, and this holds for complex algebraic operations as well. Apparently, natural language does not play any significant role in the processing of numerical information. Meanwhile, the hypothesis of linguistic relativity can be considered valid in its weak version, when it claims that a language can in certain way influence the worldview of a native speaker, but not directly determine it, as stated the stronger version. So when Chinese people who were born and raised in China but then emigrated to the United States were asked about their feelings in English, they responded in the same way as natural Americans, in terms of self-description, emphasizing their individuality in full accordance with the characteristics of the individualistic type of state's culture. When they were asked the same questions in Chinese, they described their feelings in terms of social milieu, in full accordance with the peculiarities of collectivist type culture of Eastern states dwellers, which gives particular importance to the place and status of a person in the system of social relations. Moreover, the Chinese tended to classify objects with the help of functional relationship. This was especially evident in children, while the Americans did so with the help of taxonomic categories. Thus, language is not just a tool that allows you to materialize human thoughts, but determine their expression in terms of correlation with a certain cultural context. If, however, the fact of gene-cultural interactions kept in the mind, then the nature of the activity of human genome acts as a kind of moderator, which speak in favor of the correlation of brain activity with the specifics of cultural environment. Gene-culture interactions are feasible when culture understood as the process of replication of traits and learning useful for collective existence in the case of sufficiently highly developed families of living systems, from orangutans to cetaceans and from birds to dolphins. Moreover, some forms of proto-sociality and elements of learning in the sense of achieving previously absent modes of behavior responses to external stimuli, fixed at the genetic level, observed even in insects. Cultural and language peculiarities influence the rate at which numerical representations are formed and expressed in digital form. Thus, Chinese children master arithmetic concepts and operations earlier than European ones due to the wide use of abacus in teaching, graphic properties, and compact coding of numbers in Chinese. Some human cultures use languages devoid of words expressing numerical ratios. These are non-numerical cultures whose carriers actually live exclusively by hunting, but the cognitive potential of which is associated with adaptation to the environment is not inferior to the representatives of numerical cultures. In the languages of carriers of this kind of culture, there are practically no numbers. The latter appears only at the stage of development of society when people begin to systematically engage in agriculture. Nevertheless, speakers of languages with known numerals have the ability to establish the equality of sets with a certain accuracy, to recount small groups of objects, and even to perform some simple arithmetical calculations. The same feature, meaning subtraction and addition, a kind of proto-arithmetics, observed already in a 5-month child. Children learn counting and the idea of specific numbers as a result of a fairly long study. There is ethnographical evidence to support the view that supertized and higher quantity concepts develop before their associated vocabulary and that they develop through interaction with material culture. Describing the mechanisms of the emergence of abstract objects, we can say that they are the result of adaptation to a certain instrumental practice. The presence of such objects cannot be considered a distinctive feature of mathematics alone. These are byproducts of the adaptation process, to which we owe an eminent involvement in instrumental practice. In any case, one can confidently assert ontological and activity priority in the emergence of both the concept of number and, in general, the procedures associated with abstractions. Low-level abstractions that are emerged in the process of everyday activity under certain conditions can act as a basis for higher-level abstractions and formal systems of any complexity. Language turns out to be the result of non-trivial interaction between three adaptive systems: culture, learning, and biological evolution. And both culture and the learning process significantly affect the trajectory of the evolutionary process and set the contours of the phenotype. Number sense and mathematical skills. A study of the dynamic of neural activity of the major mathematicians has shown that this activity, while performing complex and non-trivial mathematical procedures and sense of number, is located in virtually the same parts of the brain, which has nothing to do with the activity of the areas that are excited when using language. Mathematical ability is not correlated with linguistic ability. Mathematically gifted people have an increased content of the gray matter of the brain compared to those successful colleagues who are engaged in other fields of science. We can mention in the facts of rather evident genetic inheritance and the activity of the anterior parietal lobe and the inferior parietal lobe of the cerebrum in generations of gifted mathematicians. Certain contribution to the sense of number is also made by the topological features of their representation, bearing in mind the internal and external characteristic associated with relations between sets and functions of these representations are concentrated in the parietal cortex. It is important to realize that our modern representation and ordering of numbers using the number line, which stretches from minus to plus infinity, and is already known to young children, school children, is not a natural idea at all, but artificial, acquired at a rather advanced stage of human development, and mathematics as well. Only in the 17th century, Wallis and Napier proposed a system of immersion of a set of numbers in a continuous horizontal line. The image of a set of numbers in the form of a geometric line is culturally generated, which has come a long way of recognition and was established thanks to the spread of the ideas of Richard Dedekind and Georg Cantor only at the beginning of the 20th century. This image has powerful visual potential, but is not an inherent artifact. Today, it seems to be self-evident and in this sense a priori representation of this number. We meet here the fact when a subtle but effective factor has turned from a mathematical unit into a universally significant cultural image that can be attributed directly to human neural networks. Actually, the number line does not belong to the innate traits. It is cultural experience that has been transformed into a kind of mental artifact. Other numbers, other system of numbers, complex numbers, quaternions, cardinal and ordinal numbers, p-adic numbers, hyper-real numbers, and so on, became mental artifacts of the same kind, only significantly more abstract in nature and therefore not so generally significant. Apparently, the advanced digital abilities of a person are not given by nature itself, innate or hardwired networks of the brain. They are generated exclusively by the human mind, which develops in a certain cultural environment due to the influence of many social races. A social mind acquires the ability to generate the so-called conceptual metaphors, which represent simple interdisciplinary connections and acts as tools for understanding the world. Thus, the nature of the number includes both a priori and activity components. This is precisely the idea of the concept and methodology of activity-based transcendentalism, which allows us to combine Kantian a priorism, reassessed from a modern viewpoint, and an approach that declares activity to be ontologically more fundamental formation than the existence of particular objects. A holistic panorama of numerical cognition, including the recognition of the ontogenetic origin of number, the emergence of the concept of number, and the variety of numbers, as well as operation with them, arises when we consider the system, brain, culture, society, cemented by feedbacks between all its elements. The context of the idea of biocultural so-called constructivism means that each element of this system determines the activity of the rest of its elements. In the context of this idea, the brain turns out to be that active component that on the one hand determines the characteristic of the dynamics of both culture and society, and on the other hand directly influenced by both the surrounding biological environment and socio-cultural realities, vigorously transforming its state. Numerous neurophysiological studies of early arithmetic counting and or some kind of mathematical exercises show that these exercises play an undoubtedly significant role in the successful development of mathematical abilities at an advanced age compared to when these classes were not conducted. If a child masters numeracy well and demonstrates success in mathematics, then with a significant degree of probability he will be more successful not only in his further mathematical and even academic career, but also in life in general. Kant believed that pure mathematics is a priori in nature, since its provisions are universal and necessary, and they are not related to the experience. At the beginning of the 21st century, however, the progress of modern neuroscience forced to remember and re-evaluate Kantian providence. The phenomenon of subitation and the sense of number, sense of place, received ontological status. The peculiarities of the brain processing of numerical and digital information speak in favor of the fact that the Kantian research program in modern neuroscience is not just a metaphor, but an expression of the strategic line of its development. A number is not just a tag that represents a set of objects, but a result of cultural and biological adaptation to the environment, which presupposes a significant activity component. Number arises as a result of dense interaction of ontogenetic, epigenetic, and cultural factors. This understanding of a number is the sign of the naturalistic turn in modern science, which goes side by side with social centrism in modern cognitive research. Thank you for your attention.